folks, this week you're going to be learning about quadratic functions and applications of quadratic functions, and then the beginnings of polynomial functions, looking at graphs of polynomial functions. So the first thing we'll take a look at, and we'll do a quick overview of, will be quadratic functions. So let me write the following down. That's what a quadratic function looks like. F of x equals ax squared plus bx plus c. A, b, and c are all real numbers, but a is not 0. So I need you to know that. That's something you need to know. What I really need you to know is that when you have a quadratic function, what its graph will look like. First off, its graph is called a parabola, and the parabola will either be what I call a happy parabola or a sad parabola. And you'll always be able to determine if it's a happy parabola or sad parabola before you even begin to do the graph by looking at this number here, whatever a is. If a is a positive number, if it's greater than 0, if it's a positive number, then the graph, the parabola, will have that kind of shape. It's happy. Looks like a smile. If a is a negative number, so if a is less than 0, a negative number, then the parabola will have this kind of shape. So if a is positive, it's opening up, it's happy. If a is negative, it's opening down, it's sad. So I need you to know that. You also need to know an important point on every parabola. Probably the most important point on any parabola here, and for a sad parabola it'd be here, is a point that's called the vertex. So notice if you have a happy parabola, if a is positive, the vertex is kind of like at the bottom. It's at the low point of the graph. The vertex will be said, we call it a minimum. Whereas if a is negative, and you have a sad parabola, the vertex is, well, it's at the top of the graph. We're going to call that a maximum. And that's it's really important that you be able to find the vertex for a parabola. So you're going to see there's a little formula to find the x-coordinate of the vertex. And that little formula is just to find the x-coordinate of the vertex is negative b over 2a. So whatever this number is here, b, you'd put it into this formula right here for b. Whatever a is, you'll put it in here. And that gives you the x-coordinate of the vertex. So it's telling you the x value where the vertex is occurring. To get the y-coordinate of the vertex, because you're gonna need to be able to find the x-coordinate and the y-coordinate. To get the y-coordinate of the vertex, you're going to take whatever this number is. After you do negative b divided by 2a, that'll give you a number. You're going to take whatever that value is, and you're just going to toss it into the function for the x. In other words, you're going to evaluate the function at negative b over 2a. So whatever the number is, toss it in here for the x's, and that'll tell you the y-coordinate of the vertex. Some other little facts about parabolas. Well, let's try to squeeze some facts in here. Domain is all real numbers. So for any quadratic function, and the graph, this is a quadratic function, the graph is parabola. The domain is all real numbers. The range, well, if it's a happy parabola, the y value here will be the smallest number in the range. So if it's a happy parabola, the range would be whatever the y-coordinate of the vertex is. So I'll write y-coordinate of vertex to infinity. If it's a sad parabola, the y-coordinate of the vertex, well, that's the largest number in the range. So here, for a sad parabola, the range will be negative infinity to the y-coordinate of the vertex. There would be a square bracket around that. Other important things to find when we start to look at the graphs of quadratics, we're going to get parabolas. Besides finding the vertex, it's important that you find the x-intercepts, if they exist, and the y-intercepts. Remember, to find the x-intercept, you'd let y equal 0, and to find the x-intercept, to find the x-intercept, you let y equal 0. To find the y-intercept, you're going to let x equal 0. Let's do an example. Okay, these would be things that I want you to know before you do any work whatsoever. First, the graph of this is a parabola. Since a is 1, that's a positive number, you know the parabola is a happy parabola. So you know the shape of this graph. It's a happy parabola. So without doing any work, that's what the graph looks like. The vertex will be a minimum value. We haven't found the vertex yet, we haven't done anything, but we have an idea of what the graph should look like. So with that said, why don't we go ahead and find some of those important points. So I would start off by identifying the vertex. So now remember, the x-coordinate of the vertex is found by doing negative b over 2a. So for this problem, b is negative 6. So the opposite of negative 6 is positive 6. Over 2 times 1, a is 1. So it's 6 over 2. The x-coordinate of the vertex, is 3. To get the y-coordinate, you take this value and toss it into the function for x. So the y-coordinate of the vertex is found by doing the f of 3, and that gives us a 3 squared minus a 6 times 3 plus 8. That's a 9 minus 18 plus 8. Should be a negative 1. So the vertex is at the point 3, negative 1. Let's find the intercepts. So let's come over here and let's find the y-intercept. Remember, you find the y-intercept by letting x equal 0. So look at your function. You're going to toss 0 in for all the x's. Well, 0 squared is 0. 6 times 0 is 0. 0 minus 0 is 0. 0 plus 8 is 8. So the y-intercept is, we just quickly determined, is the point 0, 8. To get the x-intercepts, that's where you let y equal 0. So you're going to put 0 in for f of x. Remember, y is f of x. So that gives you this equation to solve. 0 equals x squared minus 6x plus 8. I believe that factors to x minus 4 times x minus 2. So if you set each factor equal to 0, you're going to get x is 4 and x is 2. So the x-intercepts are at the points 4, 0 and 2, 0. So the x-intercepts are at 4, 0 and 2, 0. The y-intercepts at 0, 8. And the vertex is at 3, negative 1. If we plot those points, the vertex is at 3, negative 1. So 3, negative 1 is about right there. Y-intercept at 0, 8. That's about right here. X-intercepts at 4, 0 and 2, 0. There's 1, 2, 3, 4 points that must be on the graph. And remember, we identified early on that a was 1, a positive number, so it's a happy parabola. So I should get a graph that looks something like that. And then of course you could always label the vertex, write the coordinates 3, -1. But that's all I'm going to do for this one. So that's how you would graph a parabola that's of the form ax squared plus bx plus c. Okay, here early in the chapter in graphing parabolas, the book will also show you this as the general form for a quadratic, for the graph of a parabola. In fact, I think your book calls this the standard form. And there's some benefits to having the standard form. First off, let's talk about how we know if this graph is going to be a happy or sad parabola. It's exactly what I just told you. If this number here, a, if it's positive, if it's greater than 0, you're going to have a happy parabola. If it's negative, if it's less than 0, you're going to have a sad parabola. So that hasn't changed. What has changed is that if it's in this standard form, the vertex, you can directly read the vertex is at the point hk. So that's a benefit of when we are in standard form. Domain is all real numbers. Range is still determined by, the y-coordinate of the vertex and whether or not it's a happy or sad parabola. So everything I told you about domain and range is still true. I just want to point out something that I would not do. Folks, this is, I don't want you to do extra work. If you are given, let's look at an example. If you are given this, and you're asked to graph it, you're asked to find the vertex, is it a happy or sad parabola, the x-intercepts, y-intercepts, domain, range. If you're asked to do everything, don't think you have to take this form and go through the process of completing the square and get it into this standard form. You don't have to. I just showed you how to graph this one and how to use the vertex formula. I showed you everything about this. So if you're given something like this, attack it the way I just showed you in this video. On the other hand, if you're given the quadratic in this form, x minus 2 quantity squared plus 3, in the standard form, just start off by saying, well, the vertex is at 2, 3. A is positive, so it's a happy parabola. So look at what you would have. There's the vertex. It's a happy parabola. Are you going to have x-intercepts? Well, the answer is no. It's a happy parabola. The vertex is the minimum value. So the graph's going to do something like that. Don't try to find x-intercepts. They don't exist. But you could find the y-intercept. And remember, you find the y-intercept by letting x equal 0. So you put a 0 in for the x. 0 minus 2 is negative 2. Negative 2 squared is 4. 4 plus 3 is 7. So that's up here, well off my my scaling here. But you could get a quick sketch of what the graph would look like. So in summary, at the beginning of this chapter, you're going to see a lot of stuff about quadratics and graphing parabolas. I consider that there are two types of forms. The first form I showed you, the f of x equals ax squared plus bx plus c. And I worked out example on how to do that graph. And then there's the standard form. I would not take this and do all that unnecessary work to put it into the standard form. So that's what you're going to see at the beginning of the chapter. This is what you're going to see at the beginning of graphing parabolas. Next up we'll be looking at applications of quadratic functions. And what I thought I'd do is I'd just do a couple of the homework problems that's in your book. So the first one I thought we would do is number 1. That's on page 4.2-19. So what I encourage you to do right now is pause the video, log into the MyMathLab site, open up your e-text, and read this problem. Problem number 1 on page 4.2-19. Because that's what I'm going to work through right now. So go ahead, pause the video. I'll wait for you. I'll be here. Okay, in number 1 on page 4.2-19, it says a baseball player swings and hits a pop fly straight up in the air, and, well, the catcher ends up catching the ball. The height of the baseball in meters, t seconds after it is hit, is given by the quadratic function h of t equals negative 4.9 h squared plus a 34.3 t plus 1. And then you're asked, how long does it take for the baseball to reach its maximum height? Baseball's going up, so how long to get to the maximum height? And then what is the maximum height? Okay, now look at this quadratic function. First off, h of t tells you the height. Well, it helps if I have a t there. H of t tells you the height for any time t. So if you wanted to know the height of the baseball after 2 seconds, you'd put a 2 in for the t's, and that would tell you how high the baseball was off the ground. Secondly, look at the quadratic function. The number here, a, it's a negative number. That tells us that the parabola is a sad parabola. So if we were to look at its graph, its graph is doing something like this. So what we're being asked to find here is the vertex. The value of the independent variable, t, will tell us how long it takes to get to the highest point, and then the y-coordinate will tell us what the highest point was. So really in this question, what you're being asked to do, quite simply, is find the vertex. Okay, we had just looked at the formula for finding the x-coordinate of the vertex. That was x equals negative b over 2a. That's the formula when x is the independent variable. Here, t is the independent variable. Big deal. The formula is still the same. Negative b over 2a. Doesn't matter if it's an x or a t, it's the independent variable. That's the part that's important. So if we crank it through this little formula, let's see, b is 34.3, so I'd have a negative 34.3 over 2 times a is negative 4.9. So I get a t to be, if I crank this through my calculator, and I already did that, I get t to be 3.5. Well, 3.5 what? It's going to be 3.5 seconds. But that's what the t coordinate of the vertex is. It's 3.5 seconds. So how do we get the y coordinate of the vertex? Just like we did before. We take this value of t, toss it in here for t to get the y coordinate. So basically we're just evaluating the function at 3.5. So I'll write down what that looks like. And again, if I crank this through my calculator, I end up getting 61.025. So, the vertex is 3.5, 61.025. And the vertex answers both questions here. The first question, how long does it take for the baseball to reach its maximum height? That's this value here. So that's 3.5 seconds to get to the maximum height. Then the second question, what is the maximum height obtained by the baseball? That's the y-coordinate of the vertex. The maximum height is 61.025, and it was meters, so 61.025 meters. So when you read a question like this, when you read one of these word problems, just kind of think, what is it that I'm really being asked to find? And when I see buzzwords like maximum height, maximum, or if I were to see minimum, I'm thinking vertex when I have a quadratic. That's what I'm thinking is vertex. So that's number 1 on page 4.2-19. Hey folks, the next one I thought we'd look at, like this applications of quadratic functions, is number 22. And that's in your e-text. It's on page 4.2-25. So at this time, I strongly suggest you go ahead and pause the video and go read the problem, because that's the one we're going to do. So pause the video, read number 22 on page 4.2-25. I'll be here when you get back. All right, in number 22, Jim, he wants to build a rectangular parking lot along a busy street, but Jim only has 2,500 feet of fencing available. Okay, we don't need any fencing along the street. We want to determine the maximum area of the parking lot. Okay, what your book kind of did for you here was it has a little figure in here, so you can see cars in the parking lot and cars on the street. I'm not going to draw the figure. I'm just going to kind of draw what the general shape looks like. This is the rectangular parking lot. Here's the street. I don't need any fence along the street. I need some fence here, fence here, fence here. I don't know how much fence I'm going to put here, here, or here, but I do know this. If I put X feet of fence here, and because it's a rectangular parking lot, I would have to put X feet there. Rectangular parking lot, those two sides have to be the same. I don't know how much feet's going to go up here, so let me just call it Y. Alright, now let's see what else is going on here with Jim and his parking lot. Well, let's look at the perimeter of his parking lot. Remember, there's no fence along the street. So the perimeter of his parking lot is X plus Y plus X. Well, X plus X is 2X. So the amount of fencing he's going to use for the perimeter is 2x plus y. But wait a minute, we knew he has 2,500 feet of fencing available. So that means the 2x plus y, that has to total 2,500 feet. So why don't we put a 2,500 in here for the p? Alright, that's kind of cool. But look at the question. We want to determine the maximum area of the parking lot. So I probably should get an area statement here somewhere. So let's look at this rectangular parking lot. It looks like its area is simply x times y. Area is length times width. This is what I want to try to maximize. I'm trying to maximize the area. And here's a problem. I have two variables here, x and y. But look over here at your perimeter equation. We have 2,500 equals 2x plus y. Notice if I subtract 2x from both sides, so here I go subtracting 2x from both sides, I've solved for y. I can now take this 2500 minus 2x and I can toss it right back into my area equation for y. So I'm going to take this 25 minus 2x and I'm going to toss it in here for y. And I now have the area of this parking lot written as simply a function of one variable. And if you go ahead and distribute that x, you're going to get 2500x minus 2x squared, or I would rewrite it as negative 2x squared plus 2500x. This is what we're trying to maximize. We're trying to determine the maximum area. So again, buzzwords. You see maximum, you see minimum. You have a quadratic function, you should be thinking find the vertex. And that's what we have to do here, is find the vertex. And if we find the vertex, x is negative b over 2a. So here b's 2500, so it's negative 2500 over 2 times negative 2. Negative 2500 divided by negative 4, you should get 625. Now let's think about what we just found. We found x is 625. We have just found the one side of this rectangular parking lot is 625 feet. That's what x is. Which means this side must also be 625 feet. Well, if Jim has a total of 2,500 feet of fencing, what must the length of this side be? Well, it's simply 2,500 minus 625 plus 625. Or 2,500 minus 2 times x. And that should give you 1,250 feet. So now how are you going to get the maximum area? Well, several ways. Let's go back to the first way that I mentioned. Find the vertex. You just found the x coordinate is 625. The y-coordinate, we're talking about the graph of the area function, the y-coordinate is found by evaluating the area function at 625. So you put 625 in for the x's, and you get, I'll write it down, 625 squared plus 2,500 times 625. What you get to come out here is 781,250. So the vertex, the coordinates of the vertex are x is 625 and the y coordinate is 781,250. That is the area. That's the maximum area that Jim can make with his 2,500 feet of fence. So that's one way of doing it, and then you can always check your work. I mean, folks, you know one side is 625, this side is 1250. Area of a rectangle, length times width. So if you just go ahead and do 625 times 1250, you better get 781,250. If we don't get the same answer, something bad has happened here. But that's how you would do number 22. Notice both problems I did revolved around finding the vertex of the graph of the quadratic function. So that's it for a quick look at some applications. Okay, the final topics that you'll be studying this week are graphs of polynomial functions. I would like you to know the definition of a polynomial function. More importantly, I'd like you to be able to when given a function, be able to identify it as being a polynomial function or not. The really cool thing about polynomial functions is that their graphs are smooth, they're continuous, there are no breaks in it, they're well-behaved functions. So make sure you can recognize when you have a polynomial function. For a polynomial function, let's do a quick example of one. There's a polynomial function. It's going to be really important that you can do two things just by looking at it. One, identify the degree of the polynomial. Two, identify the leading coefficient. So quite simply, degree is the largest exponent you see. So for this one, the largest exponent I see is 3. So this polynomial has a degree of 3. Leading coefficient is the coefficient with the term that is determining the degree. So here, the leading coefficient would be 4. This term was giving me the degree of 3, so that coefficient with that term is a 4. Leading coefficient will be the first coefficient you see if and only if your polynomial is written in what's called a descending order. Descending order is when, this polynomial is written in descending order. The exponents are going from large to small. Exponent of 3, 2, 1. They're stepping down. That's descending order. So if you see, let me write up another polynomial. You see something like that. This polynomial is not written in descending order. But you should be able to look at it, and you could do one of two things. You could rewrite it so it is in descending order. There's nothing wrong with that. But you don't have to rewrite it. You should be able to look at it and say, well, the degree is 4, because that's the largest exponent we see, and the leading coefficient is 8. It's the coefficient with the term that was determining the degree. So being able to determine the degree and the leading coefficient are really important, as we're going to see here in a minute when we talk about something called the leading coefficient test. Folks, here we go with the leading coefficient test. The leading coefficient test requires you to be able to determine the degree of your polynomial as well as the leading coefficient. So your degree of the polynomial, remember degree is the largest exponent you see, the degree is going to be one of two types of numbers. The degree is either going to be an even number or the degree is going to be an odd number. Let's look first if the degree is an even number. If the degree is even, so if you have an even degree, and the leading coefficient is positive, then the end behavior of the graph, and when we say end behavior, we're talking about the far extremes of the graph, not what's happening in here. Both ends of the graph are going to be shooting up. I mean, I don't know what's happening in here, I just know both ends are shooting up. If the degree is even, and the leading coefficient is negative, the end behavior of the graph, talking about the extremes of the graph, both ends are going to be shooting down. I don't know what's going on in here, I don't care right now, it's just what's happening at the extremes. Both ends are shooting down. So I need you to know this. If the degree is even and the leading coefficient is positive, both ends are shooting up. If the degree is even and the leading coefficient's negative, both ends are shooting down. Hey, now let's take a look at what's happening if your degree is odd and the leading coefficient's positive. We just reviewed when the degree was even, what was happening with the end behavior of the graph. Now we're going to look at what's happening when the degree is odd. So if your degree is odd and the leading coefficient is positive, leading coefficient positive, odd degree, this end is shooting up, this end is going down. Again, I don't know what's going on in here. We're talking about the extreme behavior. I mean, the graph could come out and do something like that. It's just that this end eventually is shooting down, this end is shooting up. If your degree is odd and the leading coefficient is a negative number, so the degree is odd, leading coefficient's a negative number, that end is shooting up, and here we're shooting down. Again, I don't know what's going on in here, don't really care. Right now we're talking about the end behavior of the graph. So to recap, if the degree is odd, the leading coefficient is positive, down, up, degree odd, leading coefficient negative, this, and this. So it's important that you know this, know your leading coefficient test. Do an example here to make sure you really are dialed into it. Hey folks, let's do a quick example here. I'm going to sketch up a couple of graphs, and in this example, I just want to know the degree, whether the degree is even or odd, and whether or not the leading coefficient is positive or negative. So the first one looks something like this. This is the graph of some polynomial function. I don't know what the polynomial function is. But look, both ends are shooting down. Since both ends are shooting down, that tells me that it is an even degree polynomial, and the leading coefficient is negative. If both ends were shooting up, I would know it's an even degree and the leading coefficient was positive. Here's a graph of a polynomial function. I don't know what the function is. I don't care. But because one end is shooting down and one end is shooting up, I know it's an odd degree. So this is an odd degree. And because this is the end that's shooting down and this one is shooting up, I know it's an odd degree with a leading coefficient that is positive. So that's how I use my leading coefficient test to determine what's called the end behavior of graphs. Okay, as we pursue more in-depth study of polynomials, you're going to learn about these things called zeros. Keep in mind that zeros of a function are nothing more than the values where the function is equal to 0. In other words, graphically, they're the exact same thing as x-intercepts. Once you start talking about zeros, then you're gonna be hit with this word. The book's going to talk about multiplicity of the zeros. So a zero could have a multiplicity of 1, a multiplicity of 2, a multiplicity of 3, etc. Multiplicity is just a fancy way of saying how many times does it occur? How many times does the zero occur? So for example, if we look at the function, x squared plus a 2x plus 1, and I'm trying to find its zeros, well, this function factors to x plus 1 times x plus 1. I set each factor equal to 0. I I get x is negative 1, x is negative 1. So the 0 for this function, the 0 is negative 1. That's the value of x that makes the function equal 0. And we would say it has multiplicity of 2. It occurs twice. It occurs 2 times. That's what multiplicity means. Now what's kind of cool about this multiplicity when it comes to the graph, when we start to look at graphs of polynomials, that if your multiplicity, so if the multiplicity is an even number, like here it was an even number, multiplicity of 2. If it's an even number, the graph just touches the x-axis. If the multiplicity is odd, then the graph will cross the x-axis. I mean, if you look at the graph of x squared plus 2x plus 1, if you look at the graph of that function, the graph is doing something like this. It just touches the x-axis at the 0 of negative 1, at the x-intercept of negative 1. And that's because the multiplicity is an even number. If you have an odd multiplicity, it actually would cross the x-axis at whatever the 0 is. So let's try to tie some of this together. So we're going to try to tie this together by finding zeros and then classifying if, the multiplicity of the zeros. All right, here we are, folks. We're going to try to tie some of this stuff together now. We're going to graph the polynomial function f of x equals x to the 4th minus 2x cubed minus 3x squared. Here are things that I notice right away. The degree is even. The leading coefficient is positive. So I know when I'm done with my graph, I better have both ends shooting up. That's using the end behavior, the leading coefficient test to determine the end behavior. So what I'm going to do now is I'm going to determine the zeros of the function because those give me the x-intercepts. So remember, zeros and x-intercepts are the same thing. So here we are setting the function equal to 0. That allows me to find the zeros, the x-intercepts. And, well, here I can factor out an x squared. And I think it factors a little bit more. I think this factors to x minus 3 times x plus 1. Set each factor equal to 0. And we get 1 0 of x equals 0. And this has a multiplicity of 2. This says x equals 0, x equals 0. That's what x squared means. So this has a multiplicity of 2. Here we have x is 3, and that just has a multiplicity of 1. And here we have negative 1, and that has a multiplicity of 1. It only occurs once. So let's try to sketch a graph. So first off, I have my x-intercepts. I know x is 3 is an x-intercept, so let me plot that. I know x is negative 1 is an x-intercept, so let me plot that one. And we have x equals 0 is an x-intercept. So let me plot that. There it is. X is 0. I know both ends of my graph have to be shooting up because it's an even degree polynomial with a positive leading coefficient. At these x-intercepts, the graph has to cross the x-axis because they have odd multiplicity. One's an odd number. At this x-intercept, the graph has to just touch the x-axis, not cross it, because the multiplicity is an even number. So I think the graph is going to do something like this. It's going to come in, it's going to cross the x-axis at the 0 of -1. Then it has to turn around and come up and hit the 0, but it's not going to cross the x-axis here because it's an even multiplicity. So it's just going to touch it, and then it's going to come back down, and then somewhere it has to turn and cross the x-axis there. And that's a very, very rough sketch. That's all I wanted right now is a rough sketch so we could see these zeros have odd multiplicity and the graph crosses the x-axis. That 0 had even multiplicity and the graph just touches it, does not cross the x-axis. Probably look at one more example here. Alright folks, here in the final example I'm kind of turning things around on us. I've given us the graph of a polynomial function. Don't know what the polynomial function is. I don't care what it is. Based on this graph, can we find the zeros? And, you know, this is scaled by ones, so that would be a 3. This is -1, this is -3. So it looks like -3 is a 0. -3 is a 0. Looks like -1 is a 0. And it looks like 3. It too is a 0. Now let's identify the multiplicity of each of these zeros. What could the multiplicity of -3 be? Well, since the graph crosses the x-axis there, the multiplicity has to be an odd number. So the multiplicity of this 0, it could be 1, it could be 3, it could be 5. The same thing for the 0 of out here at 3. The graph crosses the x-axis, so it has to have odd multiplicity. So the multiplicity of 3 could be 1, it could be 3, it could be 5. What about the multiplicity here of -1? Well, the graph just touches the x-axis there. So it has to have even multiplicity. It could have multiplicity of 2, or 4, or 6. But we know that the multiplicity here is odd multiplicity. This one is even multiplicity. And this is odd multiplicity. So what if I ask you the following question? What is the smallest degree for the graph of this polynomial function? The smallest degree. Well, both ends are shooting up, so it's got to be an even polynomial. Smallest degree. Well, the smallest degree would correspond with the multiplicity of this 0. Since it's odd, it would be a multiplicity of 1. This one would have to have an even multiplicity. Smallest for that would be 2. And the smallest for this one would be 1. 1 plus 2 plus 1 is 4. So it looks like the polynomial with smallest degree that would match with this graph, it would have a degree of 4. And we know the leading coefficient would be positive. So again, that's it for like this preview video, or however you're treating these videos. Hopefully they're helpful, and that's it. Thanks for watching.